Before we start today's lesson, let's go over the topics that we covered last time. Homomorphism. So we are in the middle of doing ring theory. Last time we covered homomorphisms and isomorphisms. Let's go over the definition very briefly. If we have two rings R and R prime, a map from R to R prime is what we call a ring homomorphism or simply a homomorphism if the following two conditions are satisfied. For each AB in R, this first condition, phi of A plus B is equal to phi of A plus phi of B. Essentially, it's saying that it's a homomorphism. This mapping is a homomorphism between the two abelian groups, R and R prime. And then the second condition, which relates to multiplication, essentially, phi of AB is equal to phi of A, phi of B. Then we went over some examples. And we say that such a mapping is an isomorphism if it is bijective. So that phi is a ring homomorphism as well as a bijection. In that case, we call it an isomorphism. Then a ring with the multiplication, where the multiplication is commutative, is called a commutative ring. So when you say a ring is commutative, what we mean by that is that the multiplication is commutative. And then this one is what we call the unity, in other words, the multiplicative identity of the ring R. And these are some of the problems and definitions that we covered. Okay. Now, if we take a ring R with unity 1, which is not equal to 0, so we are essentially excluding the trivial ring. An element U in R is called a unit of R if it has a multiplicative inverse in R. And if every non-zero element of R is a unit, if every non-zero element in R has a multiplicative inverse, we call this ring a division ring. And a field is what we call, or is defined to be a commutative division ring. So in a field, first of all, it's a ring. It's not just any ring, it's a division ring which is commutative. So all non-zero elements, they have a multiplicative inverse. Right. And then the definition of a subring. Subring of a ring R is a subset of the ring R that is a ring under the induced operation. So it's a ring on its own and is a subset of a given ring. We did several examples. Then now we are actually on integral domains. If two elements A and B are non-zero of a ring R, such that A times B is equal to 0, then we say that these two are divisors of 0 or 0 divisors. Now the ring Z has no 0 divisors because if you have the product of two integers to be 0, one must be 0. We can't have the product of two non-zero integers to be 0. Then we went over some examples where we actually saw 0 divisors. And the theorem which we proved last time, that was the last thing to discuss. In the ring Zn, the 0 divisors are precisely those non-zero elements that are not relatively prime to n. And we did the proof of this, and we had to continue from here. Right. Let's go over the proof also very briefly. So it says, in this ring, the 0 divisors are those non-zero elements that are not relatively prime to n. And we saw by example, in the ring Z6, the only 0 divisors are 2, 3, and 4, which are not relatively prime to 6. Right now, in this case, what we do? We take M to be an element in here such that that is non-zero, and we take that to be where the greatest common divisor is not equal to 1. In other words, M and N are not relatively prime. Then we can write this product M times N over D, because D is the greatest common divisor of M and N now. N over D is an integer. We have M times N over D is equal to M over D times N, which is a multiple. You see that this number ends up being N times some other integer, which is a multiple of N. So, because N over D is an element in this, this product is a product of two elements in Zn. We have the product to be 0. We have the product to be 0. That is, this product is 0. Therefore, M is a 0 divisor. This is non-zero. This is M is taken to be non-zero. So those two are 0 divisors. On the other hand, if M in Zn is such that this is relatively prime to N, for some S in N, we must have M times, when I say times, I mean multiplication modulo N, S to equal 0. Then we must have N to divide MS, the product of M and S, as elements in the ring Z. If the product modulo N is equal to 0, that means you simply take the integers M and S, you take the product, it must be divisible by N, otherwise it won't be 0 in the ring Zn. And because M and N are relatively prime, we must have N to divide S, so that S essentially is 0 in this ring. Right, so moving from this, the next corollary, we have if P is a prime, then ZP has no 0 divisors. Right now, if P is a prime, the ring ZP has no 0 divisors. What sort of elements do we have? In this, we have all elements 0, 1, up to P minus 1. Now, P is said to be a prime, right? And if you refer to the previous theorem, it says, in this ring, Zn, now instead of n in the corollary, we have this n to be a prime number P. The 0 divisors are only those elements that are not relatively prime to n. So if you have any element over here that is relatively prime to P, that is a 0 divisor. But because P is a prime, none of these elements, 0, 1, up to P minus 1, is not relatively prime to P. All these elements must be relatively prime to P because P is a prime. All these elements which are less than P, from 0 to P minus 1, they must be relatively prime to P because P is a prime. So the result is actually immediate from the previous theorem, right? So we simply state, since P is a prime, all elements A in ZP are relatively prime to P. Therefore, by above theorem, there are no 0 divisors. There are no 0 divisors. Okay. We move to the next theorem. Okay. So this theorem tells you if R has no zero divisors, then the cancellation laws, the multiplicative cancellation laws hold. And on the other hand, if these multiplicative cancellation laws hold in the ring R, then the ring must not have any zero divisors. So let's state it. I'll just put within brackets multiplicative cancellation laws hold in a ring R if and only if R has no zero divisors. If and only if R has no zero divisors. Now, I want to state here itself that all the additive cancellation laws hold in R. This is because R under addition is a group. So all the additive inverses exist and these additive cancellation laws will hold in R. So let me write it as a remark here. Additive cancellation laws hold in R since R under addition is a group. Right. So what do we mean by these multiplicative cancellation laws? I'll state them here before we move on to the proof. If you have A, B, C in R, A times B to equal A times C, with where A is non-zero. This implies you can simply cancel out essentially what we are talking about, the cancellation loss, A from both sides and say that B is equal to C. On the other hand, if you have BA, now A is on the right, BA is equal to CA, once again with the same property with A non-zero, you have B to equal C. B to equal C. Okay, let's take a look at the proof. Let's take R to be now we have this is an if and only if statement that we have to prove. The cancellation laws hold in R if and only if R has no zero divisors. So let's first assume that R is a ring in which the cancellation laws hold. So let R be a ring in which the cancellation laws hold. We have to show that there are no zero divisors. So for some AB in R, let's suppose that their product gives you 0. Suppose A times B is equal to 0 for some A, B in R. So how do we show that R has no zero divisors? If it has zero divisors, right? That means by definition, there are non-zero elements A and B where the product of the two is zero, right? Where the product of the two is zero. If it is not, if R is a ring with no zero divisors, then that means for any two, if you have the product of any two elements to be zero, one or the other must be zero. You can't have both these to be non-zero where the product yields a zero. If you have the product of two elements in R to be zero, one or the other must be zero, right? So now, but what are we going to show? We are going to show that either A or B is zero. We will show that either A or B is zero. Right. Now, if A is non-zero, we must end up with B being zero. And similarly, if B is non-zero, we must have A to be zero. So let's suppose, or let's consider consider when A is non-zero. If A is equal to A is non-zero, then this product AB is equal to 0, which is equal to A times 0. Right? These are all the properties that we've done, we discussed in one of the previous classes. So what I'm referring to is this theorem. For any AB in R where 0 is the additive identity, right? 0 times A is equal to A times 0, which is equal to 0. So this 0, AB is equal to 0. This 0 I will replace by A times 0. When if A is not 0, we have AB to equal 0, which is equal to A times 0. And this implies so that AB is equal to A0 and because our assumption is that, we are taking our R, the ring, to be a ring in which the cancellation laws hold, we simply cancel on both sides this element A, which is a non-zero element. And by cancellation laws, cancelling out A, which is a non-zero element from both sides, we have B to equal 0, right? So when A is not equal to 0 and we have the product AB to equal 0, we end up getting B equals 0. Now, in a similar fashion, we can show that if B is non-zero, A ends up being 0. So I'll simply write similarly. If B is not equal to 0, we have A to equal 0. A to equal 0. That means we have no zero divisors because in each case, either A or B is 0. That is, there are no zero devices. There are no zero devices. So when you have a ring R where the cancellation laws hold, we end up, we don't have any zero devices in the ring. Now, conversely, we have to suppose that R has no zero devices and show that the cancellation laws hold. So conversely, suppose that R has no zero devices. Conversely, suppose that R has no zero divisors, and we have to show that the cancellation laws hold. So these laws, so let me write, has no zero divisors, and suppose AB is equal to AC with A being non-zero. We have to show that if this is the case, B is equal to C in order to prove that the cancellation laws hold. Then we go to AB equals AC. This implies that because A, B, C, they are all elements in the ring. A, B, A, C, they are also elements in the ring. It's closed under multiplication. So the additive inverse of AC exists. In other words, like I told you in this previous remark, additive cancellation laws hold in R because it's a group under addition, right? Therefore, what do? We take out AC from both sides. We have AB minus AC to equal 0. Now, what we do from here is use the distributive laws, take out A. We have this to imply A times B minus C to equal 0. Now we know that A is non-zero, right? B and C are two elements in R because negative C refers to the additive inverse of C. B minus C is also an element in R. Now we have A times another A, which is a non-zero element, times another element in R equal to 0. And we know that by the supposition that R has no zero divisors. If R has no zero divisors and the product of two elements, one of which is non-zero, gives you a 0, we must have this B minus C, this one element, to be 0. Right? So we write, since A is not equal to 0 and R has no zero divisors, we must have B minus C to equal 0. Once again, you add C on both sides to see that B is equal to C. Exactly what we wanted to show. Right? So we have AB equals AC with A not equal to 0, A a non-zero element. We end up having B equals C. On the other hand, in a similar fashion, we can show that when you have for non-zero A, BA equals CA. Once again, we end up getting B equals C, right? So let me write similarly. We can show that AB, BA equals CA with a non-zero element implies that B equals C, and we are done. And we are done. Okay. Okay. Before we move further with zero divisors, before we actually define the integral domain, let's come back to the concept of a subring. Now we previously defined for a given ring R the subring, a subring, how did we define it? We defined it to be a subset of the ring, and under the usual operations, addition and multiplication, which binary operations which are defined on the bigger ring, this subset is a ring. If the subset is a ring of its own, on its own, then that is a subring of this given ring, right? So if you're following that definition, we have to prove all the axioms for it to be a ring are satisfied. In other words, you have to show that it's a group under addition, an abelian group, closed under multiplication, all these distributive laws hold, all that in order to show that it's a subring. But we can use, by simply identifying certain things in the definition, we can give another definition for a subring, which is useful in determining given subsets of given rings to be, or to see whether they are subrings. Okay. So I'll write another definition for a subring. Okay, so the definition, a subring of a ring R is a subgroup of R subgroup under addition. Let me put under addition, because R is an abelian group under addition, right? Is a subgroup of R that is closed under multiplication. Once again, if you refer to this original definition, if you have this ring R and a subset S of R, we say that it's a subring when it satisfies all the ring axioms under addition and multiplication, which is defined on R, so that it's a ring on its own under the same binary operation. So in other words, that is a subgroup of R. First of all, when you say this is a subgroup of R, you're essentially saying it's a subset and it's an abelian group under addition. And when you say it's closed under multiplication, so the multiplication, it's a binary operation defined on R. When it's closed under multiplication, it's a binary operation defined on this subset as well. The distributive laws and everything else, they follow because those are inherent properties. Those are inherent properties. So all we've got to check is whether it's a subgroup of R and whether it is closed under multiplication. So how do we usually check that a given group is a subgroup? Given subset is a subgroup. We use the subgroup criterion. So essentially, all we have to do is use the subgroup criterion on this additive group. Take any two elements, show that it's not empty, and show that if the two elements are A and B, AB inverse belongs in this subset, right? So let me write it in words and refer to that easier that way. It suffices, or it is sufficient to check that it is not empty and closed under subtraction and multiplication. So what do we mean by checking whether that it is closed under subtraction? Right? Even if you go to this definition, it says you have to check that it is closed under multiplication, which you have to do over here as well. But what does it mean when you say it's enough for us to check that it is not empty and closed under subtraction? Now, if you compare these two, it says whatever the subset that you pick in from R will be a subring if it is a subgroup of R under addition. So how do we check that it is a subgroup? We simply use a subgroup criterion, right? Right? So you have R to be a ring. R under addition is is an abelian group. S is a subset of R. To show that S is a subgroup of R, we show that by the subgroup criterion, we need to show that first is that S is not empty. Second, for any two elements A, B that you take from S, implies that AB inverse is in S. Now, the binary operation is addition. So when you refer to the inverse of B, what we refer to is the additive inverse of B. So inverse of B is simply when I say A times B inverse, this times over here refers to the binary operation addition. So what we are actually looking at is A plus the inverse of B is simply negative B. In other words, simply put, A minus B belong in S. This is what we refer to as subtraction. So we have to check that it's not empty, closed under subtraction, and closed under multiplication. The checking for this being non-empty and closed under subtraction is essentially checking for S being a subgroup of R. So in order to show that a given subset is a subring, all we have to do is show that it's not empty, closed under subtraction and multiplication. Let's do a few problems. First problem, let's take, in all these problems, let's consider R to be a ring with unity. Ring with unity 1, which is not equal to 0. In other words, the multiplicative identity 1 is in R. Okay, problem 1. Let's define S to be the set containing all Z in R that such that ZR is equal to RZ. Every element that you take from the ring is a subring of R with unity, with 1, right? So even though I have not stated it as a problem, what we are going to do is we are going to show that S is a subring of R. What sort of elements do we have in this set S? Every element in R that commutes with every other element in R. This is what we call the center of the ring R. So let me write it. Center of the ring R. Now we have to show that S is a subring of R containing 1. It's obvious that S is a subset of R because all these elements are elements in R, right? So no other elements are in there that are coming outside of R. All elements in S will be, any element in S will be an element in R by definition. So let's let's write it clearly. S is a subset of R. And in order to show that it's it's a subring, we will show that S is not empty, closed under subtraction and closed under multiplication. Clearly, S is a subset of R. Now, we also have to show that 1 is contained in it, right? Now observe, R is a ring with unity. So 1 is an element already in R. Not only that, 1 is the multiplicative identity. So every 1 will commute every element in R by definition. 1 will commute every element in R by definition. So in other words, that means 1, this unity is in S. Observe that 1 is in S since 1 times R is equal to R times 1, which is eventually equal to 1. For all R in R. So, therefore, S is not equal to 1. So, we've shown that S is not empty and 1 is included in S. Okay, now to show that S is closed under subtraction and multiplication, let's take any two elements A, B, arbitrarily chosen elements A and B from S. Now let A and B be two elements that are picked from S. In order to show that this is closed under subtraction, we had to show that A minus B is in S, or in other words, A plus minus B, right? And A times B is also in S. We need to show that plus minus B, which is simply A minus B, and AB are in S, in order to show that this is closed under subtraction and multiplication. Okay, so how do we show that an element belongs in S? By simply showing that it satisfies the definition of this set. In other words, we had to show that for every element R that you take from the ring, A minus B times R is equal to R times A minus B, and AB times R is equal to R times AB. If you show those two equations, then by definition of S, by definition of this set S, the two elements belong in S. Right. Now, let R be any element in the ring R. We have AB times R equal to A times BR. We are simply using the associative property. These are ring axioms, right? And then B is an element in S. So for any R that you take from the ring, we must have BR to equal RB. So we must have A times RB, because B in S, B that you take from S implies that BR is equal to RB. Right? Now, once again, using this associative property, we can write AR times B. This is associativity. Once again, A is taken from S. Therefore, by definition of S, for any R element that you take from the ring, we must have AR to equal RA. A in S implies that AR equals RA. Now, using this associative property, we have R times AB. So R is chosen arbitrarily. We have AB times R to equal R times AB. So that by definition of S, AB belongs in S. AB belongs in S. So S is closed under multiplication. Now we have to show that it's closed under subtraction. A minus B times R. This is simply A plus minus B times R. Using the distributive property, we have AR plus minus B times R. This is equal to, if we go back to this theorem, one of the theorems that we did last class. Yes, sorry, this one. A times minus B is equal to minus A times B, which is equal to minus or negative AB. That is exactly what we're going to use over here. So this I can write as AR plus minus of BR. Now observe once again, A is an element in S, B is an element in S. So for any element R that you take from the ring, we must have AR to equal RA, BR to equal RB. So we simply commute these two elements. We have RA plus minus of RB. This is because AB in S implies AR equals RA, BR equals RB. This is equal to RA. This minus you can write as R minus B, simply referring to that previous theorem. Take out R using the distributive laws. We have A plus minus B, which is simply A minus B. So we have A minus B times R to equal R times A minus B. By definition of S, A minus B belongs in S. That is, S is closed under subtraction as well as multiplication. S is closed under subtraction and multiplication. It's not empty. Therefore, by definition, the one that we defined earlier, it is a subring of R. It is a subring of R. Okay. For the same problem, let's prove that the center of a division ring is a field going in this direction. Okay. Prove that. Center of a division ring is a field. Okay. So first of all, we define R now to be a division ring, right? R is a ring with unity. We take it to be a division ring. So what does it mean? By definition, every non-zero element must have a multiplicative inverse. In other words, every non-zero element must be a unit, right? So first, let's take R be a division ring containing one. This is okay. At the very beginning, I said we will consider R to be a ring with unity. So we understand one is in each ring that we are considering in all these problems, okay? R is a division ring. So by definition, every non-zero element is a unit. In other words, has a multiplicative inverse. Now we have taken R to be a division ring. We are asked to prove that the center of a division ring is a field. So let's define the center of R. I have written it as S. Referring to the previous problem, S is given to be every element in R that commutes with every other element in R. Elements in R that commutes every element in R, right? So this is the center of R. We have to show that S is a field. We need to show that S is a field. Right. What do we mean by a field? Once again, recalling the definition, a field is a commutative division ring. So we have to show that S is commutative, which is obvious. It is commutative, right? And also is a division. We have to show that S itself is a division ring, right? Now I want you all to recall you have R to be a division ring. S is a subring. Doesn't mean it has to be a division ring, right? Just because you have a subring of a division ring, the subring doesn't have to be a division ring. For example, uh, if you take the ring of integers and Q, the rationals, Z is a subring of Q, and Q is a division ring. But Z is not a division ring, right? Not all non-zero elements have multiplicative inverses in Z. But in this case, the center of the ring, if R is a division ring, will be a division ring. That we have to prove. The commutative part is pretty much obvious. For example, you take any two elements A and B in R, because those elements are all the elements that commute with every other element in the ring. AB will simply equal BA, right? First, let me finish this part. We need to show that S is a field. That is, we need to show that S is a commutative division ring. S is a commutative division ring. Now, S is clearly commutative. Right? You don't even have to write this part, but for your reference, I'll put it. if you take AB in S, we have AB to equal BA. Why is that? If you take A of an element in S, A will commute with every other element in R. B is an element in S. In other words, it's an element in R. So we have by definition AB to equal BA. So it's commutative. There's nothing to really show there. Right. Now, all we have to do in this case is show that it's a division. We already know it's a subring. In other words, it's a ring on its own. It's a ring on its own, right? So let me write that part also. S is a subring of R, so that it is a ring on its own under the same addition and multiplication defined on R, right? So it's a ring, it's commutative. All we have to show is that it is a division ring. In other words, you take any non-zero element from S, it has a multiplicative inverse in S. If you take any element in S, it should have its multiplicative inverse in S, right? Now observe, R is a division ring. So you take any non-zero element from S, it will have its multiplicative inverse in R. We have to show that this multiplicative inverse belongs in S. That's all, right? So let's start off with arbitrarily choosing any non-zero element in S. Let A be a non-zero element in S. Since A is in R and R is a division ring, its multiplicative inverse, usually denoted by A inverse, exists. Exist such that, by definition, A times A inverse equals A inverse A, which is equal to 1. We need to show that A inverse belongs in S now. How do we show that A inverse is an element in S? By simply showing that it satisfies the definition of this set. In other words, for any element R that you take from the ring, A inverse R is equal to R times A inverse. That's all we have to show. Okay, now A is taken from S, right? So we start off with, for any R that you take from the ring, we have AR to equal RA because A is a non-zero element that is taken from S, right? Because since A inverse exists, we take A inverse on both sides on the left. We have A inverse A times R, A inverse times RA. Using the associative property, we have A inverse A times R equals A inverse R times A. A inverse times A by definition is simply the multiplicative identity 1 1 times R is simply R. We over here have A inverse. I'm going to A inverse times R. Now I will take A inverse on both sides on the right. So R times A inverse R times A inverse. We have R A inverse equal. Over here, once again, A times A inverse by definition is simply the unity 1. 1 times any element in R gives you that element. So we have A inverse R. Therefore, now this R is chosen arbitrarily. For any R, this is true. R times A inverse is equal to A inverse times R. By definition of the set S, we have A inverse to belong in S. Right? That is every non-zero element, and A and a non-zero element is chosen arbitrarily. What does it mean? Every non-zero element has a multiplicative inverse in S. Element A in S and a multiplicative inverse A inverse in S. So by definition, S is a division ring. It's a division ring. S is a commutative division ring. By definition, S is a field. Since S is a commutative division, S is a field. Right. So referring to the definition of the center, we can see that the center of a commutative ring must be the ring itself. Why? When we find elements in the center, we take all elements that commute with every other element in the ring. When the ring itself is commutative, any pair of elements that you take from the ring will commute. So all the elements will belong in the center. So the center will be the ring itself. Write it as a remark. The center of a commutative ring is R itself. Now R is commutative. If we write its center S, by definition, any element that commutes with every other element in the set. What sort of, once again, referring to the definition, what sort of elements do we take? For every R, ZR is equal to RZ. When R is commutative, you take any element from the ring, this condition will hold because R is commutative. So we end up with all elements in R. This is equal to R. Easy to see. Okay, let's do another problem. Let's fix an element A in R For a fixed element A in R, where R is a ring with unity. One is in there. Define C of A to contain elements in R that commutes with A. So now, instead of taking elements in R that commutes with every element in R, we are simply fixing one element and we pick elements that commute, we pick elements from the ring that commutes with this particular element, right? We can show that C of A is a subring of R containing A. It's a subring of R containing A. Obviously, it contains A because A commutes with itself. A times A is equal to A times A. There's nothing to really show over there. But we will show that C of A is a subring of R. In order to do that, we will show that C of A is not empty, closed under subtraction, and closed under multiplication. We will show that C of A is a subring of R. Clearly, A belongs in C of A because A times A is simply A squared, which is simply A. There's nothing to really show over there, right? It's clear. To show that this is a subring, first of all, we will prove that it's closed, it's not empty. First of all, we will show that it's not empty. Observe that. One is in C of A since one commutes with A. Since one commutes with A. In other words, one is an element in R and 1 times A is equal to A times 1. Right? Therefore, C of A is not empty. Now, to show that this is closed under subtraction and multiplication, we pick two elements. Let's go with P and Q. Let P, Q be two elements in C of A. We will show that P is closed under subtraction and multiplication. Okay. In order to show that it's closed under subtraction, we have to show that we are showing P minus Q is in C of A. In other words, we are showing that P minus Q actually commutes with A. In order to show that it's closed under multiplication, we have to show that P times Q also commutes with A. Right. Now remember P and Q are taken from C of A. That means P and Q commute with A. right? So now we have P minus Q, which is simply P plus minus Q times A to equal, using the distributive laws, we have PA plus minus Q times A. Right. Now P times A, once again, using the property which allows us to take this negative out, negative times QA, right? This is equal to AP plus minus AQ. Why? Because we have taken P and Q from CFA, and this implies that PA is equal to AP, QA is equal to AQ. Now, once again, using the distributive property, we simply take out A. We have P plus minus Q. That is A, P minus Q. So we have P minus Q. This is equal to P minus Q times A. We have P minus Q times A to A equal A times P minus Q. So the element P minus Q, which is an element in R, commutes with A. By definition of CFA, we must have P minus Q to belong in A. And we have P minus Q to belong in CFA. On the other hand, when it comes to multiplication, PQ times A is equal to, using the associative property, we can write it as P times QA. This is equal to P times AQ. Why is that? Q belongs in C of A. This implies that QA is equal to AQ. Now, once again, using the associative property, we can write it as PA times Q. PA I can write as AP because P is taken from C of A. That means P commutes with A. We have PA equals AP. Once again, using the associative property, we take A times, we write A times PQ. For P and Q elements that are taken from C of A, those elements belong in R. Therefore, they not only belong in R, the product commutes with A. So by definition of C of A, we have PQ to belong in C of A. Therefore, we have C of A to be not empty. This is not empty. And P minus Q, PQ, those are elements in C of A. For arbitrarily chosen PQ elements in C of A. And so, by definition of a subring, we have C of A to be a subring of R. We have C of A to be a subring of R. Okay. Right. Now we know the center of R contains elements that commute with every element in R. Whereas C of A that we have defined is it contains elements that commutes with this one element. So it's somewhat easy to see that there is a relationship between the center of R and all these CAs for each element A that you take from R. That is exactly what we are going to prove next. Let me write, prove that the center of R is the intersection of the subrings C of A over all A in R. In other words, we have to show that S, which contains Z in R, that commute with every element in R, this is equal to the intersection of all these C of A's. Okay. Now we have to show that S is equal to this intersection. What we are going to do is, we will show that S is a subset of the intersection and the intersection itself is a subset of S. So first, we will show that, let me write, we will show that and as well as the intersection is a subset of S. In order to show that S is a subset of the intersection, we will take an element, arbitrarily pick an element from S. So let Z be an element in S. Then by definition, we know that ZR is equal to RZ for all R in R. Right? For all R in R. That is, if we simply replace this R by A, just to see that it surely belongs in the intersection, right? That is, for any A that you take from R, we have ZA to equal A Z, right? Observe, Z is taken from the center of the ring. So it commutes with any element in the ring. For any A that you pick from R, any particular A that you pick from R, it will always, Z will always commute with that element A. What does it mean? This particular Z will go in the corresponding C of A. So we can write, so that Z belongs in C of A, right? And since for any A, this element Z belongs in C of A, it has to be in every C of A so that it actually belongs in the intersection itself, right? So because Z belongs in C of A, for any A that you take from R, we have Z to belong in the intersection as well, because it belongs in each of these subrings. That is, S is a subset of this intersection. S is a subset of this intersection. Now, to show that the intersection itself is a subset of S, let's pick one element from the intersection. Now, let's take Z to be an element in the intersection. If it is an element in this intersection which runs over every element in R, Z must belong in each of these subrings, right? Then for each A in R, we must have Z in CF A. Each A in R, we must have Z in CF A. By definition, what does it mean? For every A in R, right? For each A in R, Z belongs in CF A means for every A, Z will commute with that particular A. So for any A, we will have Z times A to equal A times Z. For every A that you take from the ring. Essentially, that means Z commutes with every element in the ring. Z commutes with every element in the ring. By definition, it must belong in the center. So that Z belongs in S. Therefore, we have this intersection to be a subset of S. Right? Both these cases imply that S is actually equal to the intersection. Okay. Now, once again, when R is a division ring, there are some things that we can say about CFA. If R is a division ring, for every A that you take from R, CFA must be a division ring, as we have seen in the previous problem with respect to the center. So let me write, prove that. If R is a division ring, then CFA is a division ring for all A in R. For all A in R. Right. So what do we have to do once again? We know C of A is a ring for every A in R because it's a subring of R. Right? All we have to show that is this is a division ring. So it must satisfy the definition of a division ring. What do we mean by a division ring? You take any non-zero element in C of A, it must have a multiplicative inverse in C of A, right? Now, R is a division ring. That means any element that you take from C of A will be an element in R. Because R is a division ring, that element will have a multiplicative inverse in R. All we have to do is show that the particular multiplicative inverse actually belongs in C of A. That is exactly what we are going to do. Hmm. Observe that is a ring on its own for each A that you take from R. To show that, we only need to show that all of its non-zero elements have inverses in CFA for each A in R. This is what we have to show in order to prove that it's a division ring. Observe that R now is given to be a division ring. So for any non-zero element, the inverse exists in R, like I told earlier. Right, so let's take a non-zero element first of all. Let R be an element, no, first let's take any A, R, and for this A, let's define C of A. Every element in R that commutes with A. RA is equal to AR. Right? Let's take R in C of A to be non-zero. Be non-zero. Right? Now R is taken from C of A. C of A is a subring of R, so it's a subset of R. This particular R belongs in R. Since R belongs in the ring and this ring is a division ring, its multiplicative inverse denoted by R inverse exists in R such that R times R inverse is equal to R inverse times R equals 1. We need to show that R inverse belongs in CFA. We only have to show that this belongs in CFA. Right. Okay. If R inverse belongs in C of A, by definition of C of A, it must commute with A. So that is exactly what we are going to show. Right? Now, we know that R is taken from C of A. Therefore, we have RA is equal to AR. And this implies by taking R inverse on both sides on the left, we have R inverse R times A using the associative property as well. R inverse A, R. R inverse times R is simply 1, the unity. 1 times A is once again 1 by definition of the multiplicative identity 1. This using the associative property, I will write as R inverse A times R. Now what do? I will take R inverse on both sides on the right. So we have A times R inverse, we have R inverse A times R inverse. R times R inverse once again gives you the unity. 1 times any element gives you the element itself by definition of the multiplicative identity. So we have A times R inverse to equal R inverse times A. This means R inverse actually commutes with A. Right? Therefore, R inverse belongs in C of A. So every non-zero element in C of A is a unit. Every element in is a unit. So in other words, it has its multiplicative inverse in C of A, so that C of A is a division ring. It's a division ring. And now we go back to integral domains. Right, let's start off with the definition. An integral domain, usually denoted by D, is a commutative ring with unity containing no zero divisors. So it's a commutative ring which has one in it containing no zero divisors. Once again, what do we mean by zero divisors? Recalling the definition, for a given ring, if you have A, B elements in ring which are non-zero, but the product gives you a zero, those elements we call zero divisors or divisors of zero. Right, so let me write down the definition. An integral domain D is a commutative ring with unity 1, which is different from 0, so that we are excluding the trivial ring, and containing no zero divisors. Some examples are the ring of integers. It has 1 in it. It's commutative because multiplication is commutative. There are no zero divisors. You can't find two non-zero integers where the product gives you a 0. So Z, R, Q, the ring of real numbers, ring of integers, and then complex numbers, those are all integral domains. Then we have, as we have seen earlier, ZP, right? Where P is a prime. Let me write that also. Because we have seen that ZP has no zero divisors. We proved this earlier today. If P is a prime, then ZP has no zero divisors. It's a commutative ring because multiplication modulo N or modulo P in this case is commutative, has no zero divisors. Therefore, this is an integral domain. So we understand that Zn is not an integral domain if n is not prime. We have seen examples from last time, Z6, where we had non-zero elements which are zero divisors, right? In Z6, we saw that 2 and 3, even 4 are zero divisors. Okay, so as an example, I'll write Zn. Integral domain if n is not prime. If n is not prime. And on the other hand, we know that this particular example, let's take a look at this one. Z2, now 2 is a prime number, is an integral domain. But the matrix ring of 2 by 2 or order 2 matrices where entries come from Z2 is not an integral domain, even though this the field that you see over here is an integral domain. As an example, we have 1, 0, 0, 0, an element in this matrix ring. It's an order 2 matrix where entries are from Z2 times 0, 0, 1, 0. Once again, 2 elements from this matrix ring, and the product gives you the 0 matrix, right? We have 2 non-zero entries in this ring where the product gives you a 0. So these are 0 divisors, right? These two are 0 divisors of M2 of Z2. Therefore, even though Z2, where these underlying entries come from, is an integral domain, the matrix ring itself is not an integral domain. It contains 0 divisors. Right. So now, with this, we get to our first theorem on the integral domains. Every field is an integral domain. Not every integral domain is a field, but every field is an integral domain. Every field is an integral domain. So what do we mean by a field? Once again, recalling the definition, it's a commutative division ring. It's a commutative ring where all the non-zero and a commutative ring with unity where all non-zero elements have multiplicative inverse. So what we are going to do is to show that this field is an integral domain, we will show that there are no 0 divisors in any given field, right? There are no 0 divisors in any given field. Right. So let me write proof. Show that a field, let's take any field to be F. No 0 divisors. We will show that it has no 0 divisors. Right. So how do we do that? You take any 2 elements from the field, right? You take any 2 elements from the field and we consider its product to be 0. If the product is 0 for these 2 elements that you're taking from the field, one or the other must be 0. One or the other must be 0, right? So let A and B be 2 elements in F, and suppose that A is non-zero, right? A is non-zero. Then if we have the product AB to be 0 and A is non-zero, we must have B to be 0. What happens if B is also non-zero? What happens if B is also non-zero? Now we have 2 non-zero elements in this field where the product yields a 0 in F. So those two will be zero divisors. But if we show that B is zero and A and B are arbitrarily chosen satisfying these conditions, we can simply conclude that it has no zero divisors. Right? It has no zero divisors. Okay. Then if AB is equal to 0, we must have AB to equal 0. What I'm going to do is multiply both sides by the multiplicative inverse of A. I will simply write it as 1 over A, or we can simply go with A inverse. And simply go with A inverse. Right? Now A is non-zero. A is non-zero. F is a field. Therefore, its multiplicative inverse exists and is denoted by A inverse. So what I'm going to do is multiply both sides by A inverse, right? This is the multiplicative inverse. Now we have A inverse times A, B using the associative property. A inverse times 0 is simply 0 by definition and properties relating to 0. This gives you A inverse times A is simply 1. 1 times B is equal to 0. This simply implies B equals 0 in F. B equals 0 in F. Therefore, we simply conclude there are no zero divisors in F. Once again, going back over the proof. If it's now arbitrarily choosing elements A and B from F, and we consider its product. If A is equal to 0, there's actually nothing to prove. So what we do is we consider A to be non-zero. And we have to show that if you go in that direction, once you suppose that A is non-zero, we have to show that B is 0. Otherwise, we have two non-zero elements that where the product yields a 0. By definition, those two will be zero divisors. Now, when we say that A is non-zero with this product, the product yielding a 0, we end up getting B to be 0. Therefore, we simply conclude no zero divisors, right? So now F has no zero divisors. It's a commutative ring with unity. By definition, it's an integral domain. What do we mean by definition? An integral domain is a commutative ring with unity containing no zero divisors. F is a field, so it's commutative, containing 1. Now we have shown that there are no zero divisors. By definition, this F is an integral domain. So F is a commutative ring with unity. This is since F is a field. Containing no zero divisors. By definition of an integral domain, F is an integral domain. F is an integral domain. Now, if you look at the statement once again, every field is an integral domain, but not every integral domain is a field. For example, if you take the ring of integers, it's an integral domain, but it's not a field. because if you take 2 in the ring of integers, it has no multiplicative inverse in Z. Therefore, it's not a field. But if the integral domain is finite, then we can show that in that case, it must be a field. Even though not all integral domains are fields, finite integral domains must be fields. That is our next theorem. Every finite integral domain is a field. Every finite integral domain is a field. Okay. So, in order to show that, now we simply consider any finite integral domain. In order to show that it's a field, because this is already a commutative ring with unity, with no zero divisors, all we have to show is that all the non-zero elements have multiplicative inverses, right? We only need to show that all non-zero elements are units, because what do we mean by a field? It's a commutative division ring. An integral domain is already commutative, right? So we have to show that it's a division ring. In other words, all non-zero elements are units, or non-zero elements have multiplicative inverses. So let me write that one. We only need to show that all non-zero elements are units. In other words, all non-zero elements have multiplicative inverses. Right. Let's take D to be a finite integral domain, and we will show that all of its non-zero elements have multiplicative inverses. Right? So let's take D to be the finite integral domain. And because it's finite, let's take its elements to be of this form. Integral domain containing, we know two elements, 0 and 1, and the rest we will simply write in this order, A1, A2 up to AN. Let's take these to be the elements in this finite integral domain. It's an integral domain, it's a finite ring containing this many elements. Okay. Now, what we have to show is, need to show that for any non-zero, for A in D such that A is non-zero, there exists B in D such that, or for every non-zero, there is the multiplicative inverse, right? B in D such that AB is equal to 1, which is equal to BA, right? Right. Now, I'm going to claim, right, before we make the claim, consider these elements. Consider, for this particular non-zero A, consider A times 1, A times A1, A times A2, up to A times AN. Now see, from all these elements, we are simply excluding 0. We are excluding 0 and taking the rest and taking the product of all these elements by A. A times 1, A times A1, A times A2, up to A times AN. A is also non-zero. A is also non-zero. So 0 is not here because it's an integral domain. None of these will be 0, right? We will write it as well. Now I claim that all these elements in D are distinct, right? Uh, all the elements A times A1. Now, A1 up to AN1, they are all elements in D. So all these products are also in D because D is a ring, right? Closed under multiplication. A dot 1, A times 1, A times A1, up to A times AN, all elements in D are distinct. Why do I claim that all these elements are distinct? If any of these are the same, right? So let me write since for some ij we have a times ai equals a times aj, this will implies that cancelling out a on both sides, because if you remember, one of the very first theorems that we did, cancellation laws hold in integral domains. We go back to that theorem. The multiplicative cancellation laws hold in a ring R if and only if R has no zero divisors. Now, an integral domain has no zero divisors. Therefore, the multiplicative cancellation laws hold. Therefore, for non-zero A, if you have A times AI equals A times AJ, this would imply that AI equals AJ. So if you have these two elements to equal, they're essentially the same. Right? This is because cancellation laws hold in an integral domain. In an integral domain. Right. These are all distinct. And not only that, D has no zero divisors because it's an integral domain. So none of these, like I told you earlier, none of these products will be a zero. Why is that? A is non-zero. Once you exclude zero, all these other elements in D are non-zero. So what you see over here are products of two non-zero elements. So none of this can be zero, right? So we write D has no zero divisors and so no element A times 1, A times A1 up to A times AN is 0. If I write, because A is non-zero, A1, A2 up to AN are all non-zero, including 1, that is. So now observe, we have A times A1, A times 1, A times A1, A times A2, up to A times AN, all distinct elements which are not zero, right? So if you consider this list, right? All these elements must be some element over here in this list, excluding zero. Excluding zero. So by counting, we find that these elements are elements 1, A1, A2 up to AN given in some order, right? Given in some order. Let me write it first of all. We are trying to show that A has a multiplicative inverse, right? So if all these elements are these elements given in some order, A times A1 must equal one of these. If it is equal to 1, then we have A to equal 1, and we know 1 is its multiplicative inverse. Or if you have A times AI to equal 1 for some I, we simply see that A has a multiplicative inverse. Hmm. Okay, let me write. Therefore, by counting, we find that A times 1, A times A1, up to A times AN are elements 1, A1, up to AN in some order. In some order, so that either we have A times 1 to equal 1, in which case A is simply equal to 1, or one of these elements, one of these products, A times A1, one or the other, is equal to one of these, right? Or A times AI is equal to 1 for some I. For some I. In this case, AI is the multiplicative inverse of A. Is the multiplicative inverse of A. So in any case, A ends up having a multiplicative inverse. A has a multiplicative inverse. So it has a multiplicative inverse. A is chosen, a non-zero element chosen arbitrarily. That means every non-zero element has multiplicative inverses in D. By definition, it's a field. So let me conclude by writing. A is chosen arbitrarily. All non-zero elements have inverses in D. Since D is commutative, M containing 1, D is a field. D is a field. As a consequence, we have the following corollary. If P is a prime, then that P is a field. Now it's actually immediate from this theorem. Why is that? ZP has no zero divisors when P is a prime, right? That means ZP is an integral domain when P is a prime. It's an integral domain when P is a prime. Because it's finite, it has a finite number of elements, it's a finite integral domain. So from the previous theorem, the theorem that we just proved, we see that ZP is a field. Right, so the proof is somewhat immediate. P is prime. This implies that ZP has no zero divisors. And it's commutative, it has 1 and no zero divisors. And we have written it as an example also. There's nothing to really write. Commutative we have ZP to be an integral domain. Now this is finite. Since ZP is finite from the previous theorem, from the above theorem, we see that ZP is a field. Right, so from that above theorem, we see that ZP is a field.